Hey guys, so today we're going to be looking at locomotion in the context of space. So why is this an important area of study? I think a quote that kind of sums it up nicely is from the movie Interstellar, and it's mankind was born on Earth, it was never meant to die here. So our current scientific understanding tells us that the Earth does have an expiration date. However, as humankind, we want to progress and advance past this point, and in order to do this, we have to find a means of living outside of the Earth, and this can only be done through space exploration. And to successfully explore space, we have to be able to move in space. So we have to know, we have to have an understanding of the conditions that make movement in space different, as well as the implications that those conditions can have on the human body. What makes locomotion in space different? Contrary to popular belief, gravity does still exist as a force in low Earth orbit. However, there's no ground reaction force or opposing force, and this is what produces that feeling of weightlessness. So objects in low Earth orbit are moving at a speed which we call the orbital velocity. And when they're going at the speed, they're moving too fast to ever reach the surface of the Earth. So when a spacecraft is in this state, we refer to it as being in a state of free fall. And when a spacecraft is in free fall, the humans inside are essentially floating relative to the spacecraft. And again, because they are weightless and they have low frictional contact forces, they have to employ other methods of movement in which they're bouncing around in their environment. And they can do this with three methods of locomotion called hopping, skipping, and loping. So now onto the physiological effects of space travel. So in space, there are certain conditions, specifically microgravity and cosmic radiation, which can have profound effects at a cellular level. And this can have direct implications on the physiological systems that are involved in controlling movement. So in the neurological system, there's a decrease in resting state functional connectivity between the motor cortex and cerebellum. So essentially what we see are direct changes in the functional mapping of the brain. There are also changes in the supplementary motor areas, the peripheral nerves, and the spinal cord. In terms of the musculoskeletal system, again, because they're weightless, there's no active load on their body, specifically the anti-gravity muscles like there would be here on Earth. And with this, we see effects that are kind of similar to what we would see in bed rest. So a lack of gravity can cause a 1% loss in bone mass per month, and your muscles may atrophy by 20% after just 5 days in space. In terms of the vestibular system, there are changes that are due to changes in the stimulus to the otolith organ. So typically, the otolith organs respond to changes in gravity to give us information about body position. However, when you're weightless, the stimulus to the otolith organs is the same no matter what your body position is. And so there are many interesting changes that come up in the vestibular system, such as an increase in the sensitivity of the otolith organs. There's a change in the ability to sense body tilt. There's changes in postural and eye control, and there's more significance placed on visual cues in terms of sensory integration. Okay, so biomechanics in space. So there are biomechanical differences in terms of movement in space and on Earth. And this can be shown through the Froude number, which essentially in terms of gait is a measure that describes the relationship between movement velocity and the walking to running transition. So in space, the Froude number is lower than on Earth, and so the transition to running occurs faster. And again, this just speaks to the fact that there are biomechanical differences when talking about movement that have to be considered for space travel. In terms of bioenergetics, the biggest difference is that in space, it's actually more efficient to run than it is to walk. And this is again because of reduced gravity, which in terms of movement kind of makes weight less of a factor. And also, spacesuits can behave similarly to springs when running, which can further work to drive down the energy expenditure of running when compared to walking. So, because the conditions in space are so different from what we experience here on Earth, physiological training is necessary to ensure a successful mission. So, physiological training can be done before or during spaceflight. And there are people who actually specialize in this field, and they're called astronaut strength conditioning and rehabilitation specialists. So, a large component of pre flight training is being able to simulate the conditions in space here on Earth. An example of this is submerging astronauts in water to kind of simulate the extravehicular activities that take place in space. We also learned about the profound effect that microgravity can have on the musculoskeletal system. And so with this, exercise is necessary to maintain both muscle and bone mass. So typically exercise in space is done through a device called the Advanced Resistive Exercise Device. And this allows humans to maintain core strength and also prevent weakness upon returning to Earth.